Welcome, Algebra 1 students, to Unit 1.6, Solving Simple Equations. You are hearing the voice of Mr. May, and I will be your guide through this lesson. As always, please make sure that you have your guided notes available. We will be completing those as we proceed through the unit, and make sure to use that pause and rewind button so that you can fully complete your guided notes and make sure that you understand the content. So let's proceed with our learning targets. Learning target number 1.6a, I can use the distributive property to simplify expressions. Once again, we are going to add a few more properties that will allow us to both simplify expressions and solve equations. Learning target 1.6b, I can identify the order of operations. Learning target 1.6c, I can use the properties of real numbers to simplify expressions. Again, these properties of real numbers are the properties that we learned in previous units for both addition and multiplication. And learning target number 1.6d, I can explain each step in solving a simple equation to justify a solution method. Once again, we see the verb explain. This means that you have to have an in-depth understanding of all the concepts and principles involved with solving a simple equation. It's just not the ability to solve the equation, but to explain your rationale for each step in the process. Let's begin with some definitions. The first definition is a term, and a term can be a number. And again, that could be any of the numbers we've already classified or discussed. It could be a natural number, whole number, integer, rational number, or irrational number. It could be a variable. A term could be a variable. Again, a variable is a placeholder. Usually we denote a variable with a letter of the alphabet. Most commonly we use X or Y, but it could be any letter of the alphabet that you may see. And then it could also be the product of a number and one or more variables. And product, again, refers to the operation of multiplication. So in the case where we have a number, so again, any of our numbers, such as, let's just use 2, multiplied by a variable. And again, when we see a number multiplied by a variable, a lot of times you'll see it in this type of format, with the multiplication being implied between the number and the variable. If I were to substitute in a number for the variable x, the implication is that we will multiply the number 2 by that variable. So when we see a term, it will either be a number, a variable, or the product or the multiplication of a number and one or more variables in an algebraic expression. So there is a term, a constant. A constant is a term that does not have a variable. So if there is not a variable, then we consider it a constant. A coefficient is the numerical factor of a term. Again, this is referring to the number, not the variable. So if we were to, once again, if we were to look at this term, which again is a product of a number and one or more variables, the numerical factor is the 2. And so in this case, our 2 is the coefficient, not 2x. 2x is the entire term. The x is the variable, and the coefficient is 2. So let's look at an example. So with the example, 2x plus 4. The first question is, how many terms, or how many terms are there, the number of terms? Well, I would like for you to get in the habit of designating your terms by looking at how we can portion them so that the operations are separating each one of our terms. So in this case, the operation that we have is a plus. But what I want to do is I want to include that plus with the term after it. So in this case, we have a plus 4 or a positive 4. And when I do that, that leaves me with a 2x. And so what I can see now is that I have 2 terms. I have 1 term, 2 terms. And in this case, let's look and see if they match the definition of a term. Well, the green circle, inside that I have a 2x, which is a number multiplied by a variable, or a product of a number and a variable. So that is a term. In the red box, I have a plus 4. Well, plus 4 is a number, and a number is considered a term. And so in this case, the 4 is only a number by itself. It does not have a variable, so we would consider it a constant. So I have 2 terms, and as I just mentioned, the green circle, the 2x, the term inside the green circle, has a variable. Therefore, it cannot be a constant. The 4 inside the red box does not have a variable. For that reason, we consider the 4 our constant. And then lastly, the coefficient. The coefficient is the numerical factor of a term. Well, the numerical factor of a term, in this case, the 4 is a constant, doesn't have a variable, and so the coefficient is going to be the numerical factor associated with the variable. In this case, it's the 2, so our coefficient is 2. So we have an expression with 2 terms with a constant of 4 and a coefficient of 2. A few more examples. Example number 1. Let's look at our number of terms. Well, once again, let's get in the habit of distinguishing these using our, so there's a 2x, and we have a plus 8, and we have a plus 12, and then we also have a 3x. And so looking at these terms, we have 1, 2, 3, 4 terms. And so I'm working with 4 terms. And in these 4 terms, we have constants. So remember, constants are numbers without a variable, does not have a variable. Well, in this case, the 2 terms that do not have a variable are going to be the term 8 and the term 12. Coefficients, remember, coefficients are numbers that are multiplied by a variable. Well, in this case, we have 2 terms that have a variable. We have the term 3x and the term positive 2x. Each of those have a variable, and the number attached to the 3x term is 3, and the number attached to the 2x term is positive 2. And actually, I want to go back. I want to highlight something. It's always good practice to keep the sign with the term. This is going to be important as we begin to combine like terms, as we begin to use the properties such as the associative property to rearrange and change the order of our terms. So a good practice would be to keep the signs with the terms. And in this case, looking at the 3, there isn't an explicit positive or negative in front of this 3. Therefore, it's an implied positive. And so we'll just add the positive there. So we have a positive 3 and a positive 2 as our coefficients. And so now like terms. And so a like term is, for a definition, let's just look at it. So like terms, okay, so like terms have, so like terms have exactly that word is very important. Exactly the same variable factors. Okay, so that's our definition. Like terms have exactly the same variable factor. And so when we talk about variable factors, these are the letters that we use as kind of placeholders for numbers that can be substituted in. And it's important that we focus on this exactly. So we have to have not only the same variable, but that same variable must be to the same exponent or to the same power. And so looking at the expression that we have above, we notice that there's two terms that have variables. And so the two terms that have variables are the 3x and the 2x. Now, both of them have an x, and they are both raised, in this case, to the first power. Therefore, we can say that the 3x and the 2x are like terms. They have the exact same variable raised to the exact same power. So let's stop there and hit pause for you to work example number 2. Work it on your own. See if you can use the same concepts. And I would encourage you, you may not have colored pencils. However, I would encourage you to use the same system that I'm using on example number 1 by circling the terms that are alike, putting squares around terms that are alike, and then you can use other shapes if there's more than 2 different types of terms. You can use triangles, you can use underlines, but do your best to distinguish those terms that may be like terms, grouping them together with one shape, and other terms that might be like terms in another shape. So hit pause, work example 2, and when you're finished, hit play once again. So looking at example number 2, the number of terms. So let's look at our number of terms. We have this is the first term. We have this as the second term. And again, a term consists a lot of times that we can separate them from each other using the operation signs plus or minus. We have a -3, a +5, and a +x. And so if I were to count these, I have 1, 2, 3, 4, 5 terms. Constants, again, constants do not have a variable, and the only 2 that do not have a variable are the -3. And please double check yourself if you work this on your own to make sure that you included the sign with the number. So -3 and a +5. Our coefficients once again are the numbers that are multiplied by a variable. And so we have a variable 2x squared, or x squared is our variable. And so we have a 2. Remember, the x squared is not a coefficient. That's the entire term. Just the 2 is the coefficient. Once again, that's a +2. And now look at this in front of the -x squared. There's not a number explicitly written there. So what we can conclude is that there is a 1 in front of that x squared. So one of the coefficients is a -1. That's an easy one to miss if you're not really looking closely. And then lastly, we have another variable. It again does not have a number written in front of it, so we can conclude that it is also a 1 being multiplied by the variable, and we have a +1. So those are the coefficients. Once again, please do not include the variable as a coefficient. Do we have any like terms? Well, if you use the system of distinguishing the terms from each other and grouping them as like terms as you're determining the total number of terms, it becomes relatively clear what our like terms are. So we have two circles, so that would be a like term. So each of these two circles would be like terms. So 2x squared and minus x squared. I'm not going to include the 1 there. I'm going to write it as it was in the original expression. And one thing I want to point out, it's very tempting to include the x as a like term with the x squared. That is very tempting. However, notice when we go back to our definition of like terms, you have to have exactly the same variable factors. Well, can we say that an x is the exact same as an x squared? In this case, no, because x squared is raised to the power of 2. It has an exponent of 2, whereas the x has an exponent of 1. It does not have an exponent written, therefore we conclude that it is an exponent of 1, and an x to the first power is not exactly the same as x to the second power. Once again, I want to stress that it has to be the exact same variable to the exact same power. And so a separate term is x, but it is not a like term. Not a like term. Okay, I'm going to write that just so we know moving forward that it is not a like term with the x squared. And then finally, we have two constants which we can consider as like terms. Constants are going to be like terms. Do they have the same variable? Well, in this case, technically, yes, they do have the same variable in that they do not have one. So they are the exact same. As we move forward, I'll explain to you a little bit more in depth why they have the same variable, and it has to do with the power of exponents. But we will, for now, just conclude that these do have the same variable raised to the same power. And so once again, please remember to include the sign with each of the term. Include the sign. The distributive property. This is a very important property that we use when solving equations and simplifying expressions. And what it states is that for every real number, A, B, and C. So once again, these A, B, and C. So we have A, we have B, and we have C. For these are acting as variables at the moment. For all the real numbers, then if you have A multiplied by B plus C in parentheses, and when I say multiplied, this implies multiplication. When you have a number that is positioned next to either parentheses or a variable, the implication is that we are going to multiply. And what this is stating is that A times B plus C is the same as if we were to distribute the A to the B and the C and multiply the A times B multiply the A times C, and then add them to each other. So what it's saying is that we could, using the order of operations, we could either add B plus C and then multiply it by A, or we can multiply A times B, multiply A times C, and then add them to, we will get the same value. On this side, we're stating the same thing. It's just that it does not matter which side that the A is listed on. It could be on either side, and it still maintains the same value whether we distribute from before the parentheses or after the parentheses. Below, we have A times B minus C. What this is stating is that it does not matter if we are adding or subtracting inside the parentheses. So let's do a quick example. Let's go ahead and answer this question first. Which operation is used in the distributive property? The answer is multiplication. Multiplication. We are multiplying. So multiplication. And so let's do an example. So if I were to have 3 times 2 plus 1. Well, order of operations tells us that we could say that 3 times 2 plus 1 is 3 is equal to, in this case, 9. And so the question is, does that or is that equivalent to 3 times 2 plus 1 if I were to distribute the 3, okay? And in that case, I would have 3 times 2 plus 3 times 1, which is 6 plus 3, which is 9. These two are equal. So what is happening is that in the first case, in number 1 here, I combined the 2 plus the 1 inside the parentheses, then multiplied by 3. And in the second example, I distributed the 3 using multiplication by each term. Remember that you have to distribute to all terms. That is very important. Put a little note. Distribute to all terms. Okay, do not forget that. So I had to distribute to the 2, the 3 to the 2, and to the 1. Multiplying, remember, distribution implies multiplication, and at the end added the final 2 like terms. So example number 1, highlighting learning target number 1.6a. So looking at this first example, what we can see is that we have an instance where we can simplify this expression. I'm going to work it 2 different ways on purpose. The first way, I'm going to work it in order of operations. So we've got 34 times 102. Notice all that I have done is add inside the parentheses first using the order of operations. At this point, I'm going to multiply. The implication is multiplication now. So I have multiplication. 34 times 102 is 3,468. Now I want to compare that to distributing the 34 to all terms. When I distribute, the implication is multiplication. Okay, so 34 times 100 is 3,400, plus 34 times 2 is 68. Adding 3,400 plus 68 is 3,468. So we end up with the exact same result. whether we use the order of operations by combining what's in the parentheses first, then multiplying, or distributing, and then combining the like term constants. So hit pause and work the next two examples on your own. Actually, before you do that, let me work this next one because there is a variable included. Then you can work the last one on your own. So let's work this next example together. And in this case, what we have is we have a constant of 3 and we have a variable with a coefficient of 5x. These are not like terms, okay? So 5x and positive 3 are not like terms. Since they are not like terms, they cannot be combined by addition or subtraction. Excuse me. And so, since they cannot be combined by addition or subtraction, this expression 5x plus 3 is as simple as it will become inside the parentheses. So this is where the power of the distributive property comes into play, is because while we cannot combine these as like terms under addition or subtraction, we can distribute the 2 and simplify this expression further. And when we distribute the 2, what we are going to do, again, is multiply. So we're going to multiply the 2 times the 5x, and then add that to the 2 multiplied by the 3. Again, it does not matter which direction we're distributing, whether from before the parentheses or after, we're still implying multiplication. Now, when we multiply the number 2, by 5x, remember the 5 is our coefficient. All we are going to do is multiply the 2 by the coefficient. So 2 times 5 is 10, and then the x goes along for the ride. We do not multiply by the x, we do not multiply that 2 by the x as well, because we have an implied multiplication already between the 5 and the x, and using the associative property, we could multiply the 2 times the x and then back by the 5, which we would still end up with 10x. And so what we are going to do is just multiply the 2 times the 5, and then knowing that that x is a variable, we will leave it there as a placeholder until we have a number that we want to substitute in for that variable x. Multiplying the 2 times the 3, 2 times 3 is 6. So 2 times 3 is 6, so now we end up with the expression 10x plus 6. And so the question I ask is, are 10x and 6 like terms? Well, this is a term. The plus 6 is a term. Do they have the exact same variable raised to the exact same power? Well, x is the variable in 10x. 6 does not have a variable, so they do not have the exact same variable. So they are not like terms. For that reason, we have a simplified expression of 10x plus 6 as our final answer. And so in the example number 2 to the right, I'm not going to work it out completely, but it does not matter which direction we distribute it from, we still end up with 10x plus 6 as our final simplified expression. Now, I would like for you to hit pause and see if you can work example number 1, part 3. Okay, looking at this example, number 3, I'm going to go ahead and distinguish my terms. I've got a 7x. I have a plus 2. Remember, it's an implied plus. A plus 8 and a minus 3. The 2, 8, and 3 are like terms. Therefore, I can combine them inside the parentheses. So I could say 7x and 2 plus 8 is 10 minus 3 is 7. And then I can just multiply the 7x times the 7. Now, technically, I am distributing here. Technically. And since I am distributing, I am multiplying. And once again, when we multiply with a variable coefficient, a coefficient times a constant, so I've got the 7, and then I have the other 7 as my coefficient. I multiplied those two by each other, bringing the x along for the ride, and 7 times 7 is 49. And then the x continues to be a variable placeholder until I want to substitute in a value for it. And so 49x is the simplified expression. Looking at the part 3 on the right, once again, I could use the same methodology of highlighting my terms. I've got 3 like terms, but in this time, instead of combining my like terms, I'm going to distribute the 7x. And once again, when I distribute a term with a coefficient, I'm just going to multiply the coefficient by the constant. And so I end up with 14x plus, and then we have 7 times 8, which is 56. Remember, a positive times a positive is a positive. The x continues to come along for the ride. And now I have a minus 3 times 7, which is a minus 21x. Looking at this expression, I can now see that I have these as my like terms because they all have a variable x. All the variable x's are raised to the first power. They are the same variable raised to exactly the same power. Therefore, they are like terms, and I can combine them. And when I combine them as like terms, what I will say is 14 plus 56 is 70 minus 21 is 49. And I'm going to do something here just to highlight a particular point I want to make. When we combine like terms with a variable through addition and subtraction, we do not change the value of the exponent of the variable. It remains the exact same. So that x stays the same exponent and variable as the x in the terms that we were combining. And so in combining these like terms, we have added the coefficients. And in the case of the minus 21, we added the negative. And then the x maintains its same properties as far as the variable and the exponent. Notice finally that despite distributing first or using the order of operations, my two final answers are the same. So consider, we have a relatively long expression. And so what we can do is we can begin by first looking to see, can I combine any like terms or can I distribute? Which one do I want to do? Well, a lot of times I would encourage you to go ahead and distribute first. So where can we distribute? Well, anywhere there's a parentheses. So in this case, we can distribute the 2x to both the 3 and the minus 4. Remember, we have to distribute to all terms. We can distribute the 3. And then looking over here, we have parentheses, but there's not a number in front of it. We just have the minus sign. What this implies is that there is a 1 in front. So we can distribute, and we have to take the sign with it, we can distribute the -1. And so combining these, or I'm sorry, distributing these terms, I have 2x times 3 minus, let's just do it this way. Let's go plus 2x, because that is a positive 2x, times -4. We didn't do anything to change the x, so we'll just drop it down. Plus 3 times 6, plus 3 times -2x, minus 1 times 3x, minus 1 times 7. So all I've done is distribute it, and I've written it out in total how I distributed it. So now, simplifying further by multiplying, because the distributive property implies multiplication, I have 6x. 2 times -4 is -8x. Remember, we're just multiplying the coefficients. The x remains the same. Plus 3 times 6 is 18. 3 times -2 is -6x. -1 times 3 is -3x minus 7. And at this point, we have to look and say, okay, am I finished? Well, I know I'm finished. I've completely simplified the expression when there are no longer any like terms. So I have to look, are there any like terms? Well, let's begin. Let's see, I've got a 6x. Are there any other terms with an x raised to the first power? Well, this is a -8x raised to the first power. This is an x raised to the first power. X raised to the first power. So all of these are x's raised to the first power. So I still have a positive 18. We know that's a constant. Does not have a variable. And the -7 does not have a variable. So now I can look and say, okay, can I combine these as like terms? Well, in this case, yes, I can. And what I'm going to do is just add the coefficients for the terms with a variable. So the 6 minus 8 is -2. -2 plus 1, because this is an implied 1. So 6 minus 8 is -2. And then plus 1 is -1. And then add the -6. So add -6 is -7. And then the -3. So we end up with a -10. Remember, the x remains the same. It does not change. Looking at the red boxes, these are our constants. So I have 18 plus a -7, which is the same as 18 minus 7, which is a positive 11. So looking at this remaining expression, our -10x and positive 11, are they like terms? Are these like terms? And in this instance, no, they are not. No, the expression is fully simplified. So we are finished. Once we get to a point where we have no more like terms that can be combined, then we have finished simplifying the expression. So simplifying expressions. We're going to use the order of operations GEMDOS. Now, it used to be PEMDAS. This used to be a P, but we've become more generalized because there are multiple ways that we can group other than parentheses. So now we call it GEMDOS. And so what the G stands for is grouping, and we're going to perform any operations inside grouping symbols such as parentheses first. After we simplify our grouping symbols, we're going to look at exponents. We're going to simplify all powers. So this might be x squared or a number squared or a number cubed. We're going to simplify all of our exponents second, followed by M and D. These are we're going to multiply and divide, and in this case, we're going to go from left to right. So we're going to work our way from the left to the right, multiplying and dividing. Finally, we're going to add and subtract, and once again, we're going to add and subtract from the order of left to right. So I'm going to go back one slide, and we're going to see if we did that in our expression that we just simplified. So here's the expression we just simplified. Did we work with our grouping symbols? In this case, yes. And the way that we worked with our grouping is by distributing. So we simplified our parentheses first by distributing into them. So after we distributed and we simplified our grouping symbols, we have to ask, do we have any exponents? Do we have anything that is raised to a power? In this case, no. So we don't have to use that step. After that, we multiply and divide. Well, there's not any division, but there is multiplication. And the multiplication was between these terms. And so we worked from left to right and multiplied. And then after that, we look to add and subtract. And remember, subtraction is the same as adding the negative. And we did that with our like terms. And actually, I should probably change that to green. And we went from left to right, adding and subtracting, or adding the negative to with our like terms. And so you can see that we followed that order of operations while simplifying the previous expression. Example number 2, highlighting learning target number 1.6b. Study the expression and think about the concepts that you would use to fully simplify it. Hit pause, work through the example, and once you've completed simplifying it fully, hit play and we'll work through it together. When we consider simplifying this expression, we know that we're going to use the concepts revolving around GEMDOS and combining like terms. So we'll begin with using GEMDOS to give us a procedure or a process to work with the order of operations to fully simplify the expression. So GEMDOS referring to our groupings first. In this case, we have two groupings with parentheses. And so the way that we are going to simplify this grouping is by distributing the value outside the parenthesis that is being multiplied by it. And so when we distribute, we're going to distribute the 3 because the 3 is being multiplied by the grouping or the parentheses. And also, we know that there is an implied 1 outside of the second set of parentheses. And so we will distribute the full term -1 into the parentheses. And as you may recall, the distributive property implies multiplication, and we must distribute to all terms inside the grouping. And so we will be multiplying, in this case, the 3 times the 2x and the 3 times the -3, as well as -1 times 2 and -1 times 3x. So let's begin by first dropping down the terms that we have yet to work with or simplify, rewrite our groupings using the distributive property, and again I'm going to use parentheses here to imply the multiplication. So now we have -1 times 2, -1 times 3x, and then we're going to drop down the 2 because we have yet to work with it. Second in the order of operations are exponents or simplifying exponents. We do not have any exponents that have a power greater than 1, and so we'll continue to the next step in the order of operations, which is to multiply from left to right. So working from the left to the right, we see that we would have 5x times 2, 3 times 2x, 3 times -3, -1 times 2, -1 times 3x, and then the 2 is just an addition at the end of the expression, and we have yet to work with addition and subtraction. And so simplifying these terms, we know that when we multiply a term with a variable, that we are just going to multiply the coefficient so that we have 5 times 2, which is 10, and then the variable is just going to remain as is. We have 3 times 2x, so multiplying the 3 times the 2 is 6. The variable remains as is. Positive 3 times -3 is -9. -1 times 2 is -2. -1 times 3x is -3x. And then the positive 2, once again, is just brought down to the next line. The next step in the order of operations is division. We do not have any terms being divided, so we can move to our next 2 steps, and I'm going to combine these as addition and subtraction because the concept of subtraction being adding a negative. And so we're going to consider subtraction as adding the negative, so we're going to work the additions and subtraction operations together, moving from left to right. But in order to do that, we must identify our like terms. And remember, like terms have the exact same variable raised to the exact same exponent. And so we have a 10x, which is an implied plus 10x because we want to keep our sign with the term. And so we have a variable x to the first power. Looking at the 6x, it is also an x raised to the first power. And then finally, we have a -3x, and the x is raised to the first power. So we have the variable x raised to the first power in all of these terms. Looking at our next term that is yet to be grouped in a like term grouping, we have a -9. This is a constant. It does not have a variable, and so our other terms that do not have a variable are the -2 and the +2. So we have successfully grouped all of our like terms. Now we need to combine them. And so combining the circles, or our terms with the variable x, we have addition or adding the negative in the case of subtraction, which means that we're just going to take our coefficients and we're going to combine our coefficients. The variable remains the same. So 10 plus 6, so 10 plus 6 is 16. 16 minus 3, or added to negative 3, is 13, and our variable remains the same. And so just to show you, we have our 10 plus 6 is 16 minus 3. Working with our constants, we have minus 9 plus a negative 2, which is the same as subtracting 2, so that's minus 11. Minus 11 plus 2 is minus 9. So we have 13x minus 9. So now the question we have to ask ourselves when we are complete, when we have fully simplified it, do we have any remaining like terms? Again, that's the question you always ask yourself. Are there any remaining like terms? And in this case, no, the expression is fully simplified. And recall, this is an expression because it does not have an equal sign. Therefore, we can only simplify it. We simplify expressions, we solve equations. This particular example does not have an equal sign, therefore it is an expression, and so we fully simplify the expression until there were no remaining like terms to be combined, and all the groupings have been removed, and we have fully worked through the order of operations. What is the difference? Notice on the left we have an expression, and on the right we have an equation. What is the difference between these two? So we have an expression, and we have an equation. What do you notice as being different between the two? And you may recognize or realize two things. The first and most important is that you have an equal sign, and then that suggests that it's equal to something. And this, no equal sign. And so the difference between an expression and an equation is that an expression does not have an equal sign. That is very important. An expression does not have an equal sign. An equation does have an equal sign. And notice, a way to remember this, equation almost has the word equal in it. So when you see an equal sign, you know you have an equation. And that's important because it denotes how we deal with this particular either expression or equation. With an expression, we can only simplify expressions. There's nothing to solve for because we don't have an equal sign. We can only simplify expressions. Whereas with an equation, we can now solve equations because we have an equal. We set it equal to something. So in this case, we could solve for the variable x. So the difference between an expression and an equation is the equal sign, denoting that we simplify expressions, solve equations. And so what's the difference? Expressions do not have an equal sign, and that they are simplified. Equations do have an equal sign, and they are solved. Very important concept. Please make sure that you remember this and highlight it as one of the more important concepts going forward. Two more properties. So our two properties, the additive property of equality and the subtraction property of equality. What these are saying, and they are related to each other in the sense that they allow us to solve equations. But what they are saying is that it allows for the same quantity. The same quantity to be in the additive property, to be added to both sides of an equation. Okay, so we have to have an equation to use the additive property of inequality. Okay, additive property of equality, you must have an equation. And what it says that you can add the same quantity to both sides and not change the value. The subtraction property says that you can subtract the same quantity from both sides, once again, with an equation. Now, why does this make sense? Well, if I have an equation, what we know is that the two sides are equal. That's what an equal sign means. An equal sign means that the two sides are equal. Well, if I know that A and B are two values, okay, so we have A and B are two values, and I know that those two values are equal. Okay, so if I know that 5 is equal to 5, so 5 and 5, if I take the same value and add it to both of them, so if I take a 2 and add it to both sides, then what happens is the value changes, but both sides are still equal. So this 7 is still equal to 7. The property of equality did not change. Both sides are still equal to each other. Okay, so whenever we have an equation, we have to make sure that both sides are equal. Same occurs when we subtract. If I have 5, let's use the same color scheme. If I have 5 is equal to 5, 5 and 5, I have my equal sign and I subtract 2 from both sides. The value did change, but the equality of the two sides did not. 3 is still equal to 3. So both sides remain equal to each other. It's very important when working with an equation that both sides remain equal to each other at all times. So if you do something to the left side of an equal sign, you have to use the exact same operation on the right side of the equal sign to maintain equality. That's true with addition and subtraction, and also with multiplication and division. Multiplication, the multiplicative property of equality allows for the same quantity to be once again multiplied to both sides. And lastly, we are still working with an equation. The division property states that the same quantity can be divided on both sides of an equation. The important concept is that if you perform an operation on one side of an equal sign or one side of an equation, the exact same operation with the same values must be performed on the other side of the equal sign or the equation to maintain the equality. And the multiplicative property of equality allows us to do that with multiplication. The division property of equality allows us to do that with division. Using our same numbers, 5. So 5 and 5 times 2 times 2. 10 is equal to 10. The values did not change. Looking at, let's make it a little prettier numbers. Let's do 10 and 10 in this case. So 10 and 10. 10 divided by 2. 10 divided by 2. There's our equal sign. We're dividing both sides by the same quantity, 2. And 5 is equal to 5. So the equality of the two sides did not change. So example number 3, highlighting learning targets number 1.6c and 1.6d. What we're going to do with this particular example is we're going to use our properties of real numbers to solve our equation. In this case, we know it's an equation because I have an equal sign. So we have equal sign denotes equation. And as you may recall, we solve equations. And so we are going to work to solve this equation, and then we are going to justify our steps using the properties of real numbers as we work through this equation and solving, in this case, for the variable x. And so our first step using the order of operations would be to work with our parentheses or our grouping symbols. In this case, we cannot combine the like terms. We cannot combine these terms because they are not like terms. And so we go to our second step, which would be exponents. We have no exponents that are raised to a power above 1. So then we look at multiplication and division. There is nothing at the moment to multiply, so we need to look and see if we are working with division. Well, we do have, in this case, division by 2 on the left side of the equation. And so what I'm going to do is I'm going to put a line through my equal sign to show that the left side and the right side are separate from each other and that they must maintain equality at all times. So if I do something to the left side of the equation, I need to do that to the right side of the equation, the same operation with the same quantity or same value. So in this case, I have a 2 that is being divided. Well, now I need to look at inverse operations. So inverse operations are operations that undo the work of another operation. So in this case, the inverse of division is multiplication. So we're looking at inverse operations. And so our inverse operations, our inverse operation of division is multiplication. So to get rid of the 2 being divided, I need to multiply by 2 on that side of the equation. And what happens is that the 2 being divided by the 2 will cancel each other out. So the 2 and the 2 will cancel each other out because 2 divided by 2 is 1. And then our multiplication property, our identity property of multiplication tells us that anything multiplied by 1 is its value. And so that will leave us with 3x plus 5 on the left side. But I multiplied by 2 on the left side, so I need to multiply by 2 on the right side of the equation. And so what I used is the multiplicative property of equality to say I can multiply both sides by the same value, and in this case the same value that I multiplied by was the 2. So when I simplify that, I end up with 3x plus 5 is equal to 14. Once again, I'm trying to solve for x, which means that I need the x to be isolated or by itself. So the x is not yet by itself. I still cannot combine the 3x and the 5 as like terms. So now I need to remove the 5 using an inverse operation. I need to get the x by itself. And I'm going to work from the terms that are furthest away from my variable. Well, the term that's furthest away from my variable is the 5. And so I'm going to look at the 5, and by looking at the 5, I know that it's a plus 5. And if I want to remove the operation of addition, then I know that I can subtract. But if I subtract on the left side, I also have to subtract on the right side of the equation. And the property that allows me to do that is the subtraction property of equality. Now, anytime that you use an operation on both sides of an equal sign, you will be using the properties of equality. So when I simplify this further, I end up with 3x because 5 minus 5, or 5 plus a negative 5, is 0. And then 14 minus 5 is 9. And so I end up with 3x equals 9. 3 times x is multiplication. The inverse operation of multiplication is division, so I need to divide. And if I divide the left side by 3, I have to divide the right side by 3. And the property that allows me to do that is the division property of equality. And so I end up with 3 divided by 3. So 3 divided by 3 is 1. 1 times x is x. And so even included within this step, we have the identity property of multiplication. And then 9 divided by 3 is equal to 3. And so the final is that we have a solution because we have solved for the variable x. So you can see that we can justify each of our steps in solving this simple equation using our properties of equality. And so the final example number 4. Example number 4. Highlighting learning targets number 1.6c and 1.6d. Solve and justify each step. Hit pause, work through the example, justify each step in the process, and once you finish, hit play and we'll work through it together. So looking at the the equation, and again, we know it's an equation because we have an equal sign. And since I have an equal sign, I know that I'm going to be solving for the variable. Using our order of operations, I know that I need to remove the parentheses first. Working with the distributive property, I'm going to distribute the numbers into the parentheses. And so step number 1, we're going to use the distributive property. So the distributive property, and when I use the distributive property, I'm going to end up with 2 times 4. Remember, we only multiply it by the coefficient. So it's 8x plus 4 equals 15 minus 3x. I'm going to draw the line through the equal sign. Notice that I am keeping my work nice and neat, going directly down in columns. That way I can easily see my terms. I now notice that on the left side that I have an expression on the left side that does not have any like terms. And I also have an expression on the right side that does not have any like terms. So now I need to start moving my terms back and forth across the equal sign in order to get my like terms on the same side. Now I attempt to move in the direction of not working with minus negatives if possible. So in this case, I know that if I move the minus 3x term, the inverse operation of a negative or subtraction is addition. So if I add 3x to the right side, I also know that I must add it to the left side of the equation. Notice that I wrote it directly underneath the minus 3x or negative 3x, and I wrote it also on the left side directly under the positive 8x. I'm keeping my like terms together, grouped together. When I do that, I'm using, as step 2, I'm using the addition property. And because I went on both sides of the equal sign, it's the addition property of equality. And now combining my like terms, 8x plus 3x is 11x plus 4 equals 15 plus 0, but I do not have to add the 0 in necessarily because of the identity property of addition. Now, I notice that I still do not have all my like terms on one side of the equation. I need to move the negative 4, the positive 4. And the way that I can do that is using the inverse operation of addition, which the inverse operation of addition is subtraction. So I'm going to subtract 4 from the left side. If I subtract 4 from the left side, I must also subtract 4 from the right side of the equation. When I do that, I'm using the subtraction property of equality. And when I simplify that, 4 minus 4 is 0. I end up with 11x. 15 minus 4 is 11. And now I only have one term on each side of the equation. And on the left side of the equation, I have 11 times x. It's an implied multiplication. Well, the inverse operation of multiplication is division. So to undo the operation of multiplication, I'm going to divide by 11. The property that allows me to do that is the division property of equality. And so when I use the division property of equality, 11 divided by 11 is 1x equals 1. And just to show that you can use other properties of real numbers, 1 times x is x, and that is the identity property of multiplication. And so 1 times x is x, and so x is equal to, not x is equal to 1. And so our final step is our solution, and we know it's a solution because there is an equal sign. And so if I were to go back and number my steps, this was step 1, step 2, step 3, step 4, step 5, and step 6. So this is solving an equation and justifying each step. This concludes Unit 1.6, Solving Simple Equations. As always, please go back and review your guided notes, rework the examples, make sure that you fully understand them, and if you have any further questions, please ask one of the math teachers. We are more than happy to clarify any concepts that you may need additional help with. As always, have a great day, and we look forward to seeing you in class.